Chapter 10, we're looking at the liquids and solids and their properties. We're going to start by looking at the attractive forces that make them liquids or solids, and these are intermolecular forces, or IMF. And these are the forces between the atoms or the molecules that hold them in the solid or the liquid state. And these forces can be between ionic compounds, within metallic elements, or between covalent molecules. For solids and for liquids, they can be primarily covalent. And intermolecular forces are also referred to as van der Waals forces. So IMF and van der Waals forces are the same thing. We're going to start looking at liquids. Intermolecular forces in liquids, the least strong, we're going to start with London dispersion forces. And London dispersion forces are primarily between nonpolar molecules. And these are due to instantaneous dipoles that form between these molecules. So if we look at our two atoms, atom A and atom B up at the top, because they're nonpolar, they have a uniform distribution of electrical charge. But those electrons are not static, they are mobile. And so what we have then in the second set of pictures, atom A, the electrons in their shifting around, end up primarily on the left side of the molecule, or the atom in this case, which makes the left side of the particle temporarily negative, thus the negative delta sign, and the right side then is slightly positive or temporarily positive, thus the positive delta sign. And what that does is that induces a dipole in its neighboring molecular atom. It's instantaneous because they're continually shifting, but it looks like this. So now at the bottom we have both particles, either atoms or molecules, this can happen, where the left side is partially negative, the right side is partially positive. So between the positive on the left particle and the negative on the right particle, we have an attraction going on here. It is a polar interaction, and it is temporary because these again are nonpolar particles and the electrons are continually shifting. And this happens on down the chain. As the electrons switch their positions, the polarization either disappears completely or changes. What we find is the larger the particle, whether it's an atom or a molecule, and the more electrons it has, the more polarizable it is, because the slop of the electrons can shift. It's like swinging the water back and forth in a cup or swinging the water back and forth in a bucket. You get a larger slosh with more water. So London dispersion forces, again, are the weakest of the IMF, and the larger the atoms, the larger the molecules, the more polarizable they are. Therefore, stronger London dispersion forces. So these intermolecular forces are not just cut and dried. There is a continuous range. So we start with weak London dispersion forces, and as the molecules of the particles get bigger and bigger, or closer and closer to being polar particles as opposed to nonpolar, then their London dispersion forces get stronger. Eventually we get to a point where we have something called dipole-dipole forces. These are the second kind of IMF, second kind of van der Waals forces, and these are formed in molecules that have permanent dipoles. In polar molecules, we have a permanent positive end and a permanent negative end. They're not positive and negative like ions, but they're partial charges. They don't slop around as they would in a nonpolar molecule. And if we look at the diagram here, we have the positive end of one molecule attracting the negative ends of several molecules, repelling the positive end of another molecule. So we have both attractive forces and repelling forces going on in our dipole-dipole forces. Usually the particles, the molecules are aligned so that the attractive forces are stronger. Again, there's a range in dipole-dipole forces. When we have slightly polar molecules, they're going to have fairly weak dipole-dipole forces. They're still stronger than London forces, but they're not the best for dipole-dipole forces. In very polar molecules, we have very strong dipole-dipole forces. So again, a range. The more polar the bond, the more polar the molecule, the stronger the dipole-dipole forces. Okay, our super-duper dipole forces are hydrogen bonds. Hydrogen bonds are, again, just the super strong form of dipole-dipole forces. They exist in molecules, as the name applies, that contain hydrogen atoms. The other thing that hydrogen bonding molecules must have is hydrogen attached to either a nitrogen or an oxygen or a fluorine atom. If there's hydrogen in the molecule, if there's oxygen or nitrogen or fluorine in the molecule, but the two are not attached, there's no hydrogen bonding. So we have to have direct attachment between hydrogen and one of those three elements. The reason that these are so strong is because hydrogen, nitrogen, oxygen, and fluorine are so small. The other reason they're very strong is because nitrogen, oxygen, and fluorine are also very electronegative. So they're going to really pull on that electron in the hydrogen and that element bond. And so hydrogen's going to be almost ionic in nature. The electron's going to be almost completely pulled off it and stuck onto the nitrogen, oxygen, or fluorine. So they're very, very polar bonds, which makes them very strong. We look at the molecule or the diagram here of water molecules. Water has the properties it does because it hydrogen bonds. And so the hydrogens in one water molecule are going to be attracted to the oxygens in neighboring molecules. We're going to take a look at some of the physical properties of solids and liquids. And the two that we're going to start out looking at are the melting points and the boiling points. There's a pattern to melting points and boiling points of solid and liquid compounds. And one of the things it depends on is the atomic mass or the molecular mass. If we look at the chart here, we've got boiling point on the vertical axis and the elemental period on the horizontal axis. So if we look at period 2, we've got methane, which has a very low boiling point, which means it's a gas. And then we have ammonia, hydrogen fluoride, and water having higher boiling points. Now, all four of those elements, carbon, nitrogen, fluorine, and oxygen, are side by side. You'd think the pattern would be pretty close. The reason these three compounds have such high boiling points is because they have hydrogen bonding. In order to get a liquid to become a gas, you have to disrupt the intermolecular forces so that the molecules can separate from each other and can go from the liquid state to the gas state. Methane's nonpolar. Methane has London dispersion forces. Those are pretty weak. So it's got a fairly low boiling point. It's a gas at room temperature. The other three, much stronger intermolecular forces, hydrogen bonding, and therefore their boiling point is going to be much higher. As you can see, oxygen and in water has the strongest hydrogen bonding, primarily because there are two hydrogens attached to the oxygen. Hydrogen fluoride only has one hydrogen attached to the fluorine. So because the two hydrogens to one oxygen, that makes water the superstar in hydrogen bonding. That's not what we're talking about here when we're looking at mass, however. If we start with period 3, we take a look at the compounds as we progress. They're all hydrides, so the element combined with hydrogen. As we increase in mass, fairly predictably, we increase in boiling point. The reason for that is the larger something is, the more energy it takes to get it moving. The more mass something has, the more energy it requires to get it to change its position. Even within our hydrogen bonding group, that holds true because the mass of water is 18, which is higher than the mass of ammonia, which is 17, which is higher than the mass of methane, which is 16. Hydrogen fluoride's the anomaly. It's got a higher mass. Again, because it only has one hydrogen attached to it, its hydrogen bonding isn't quite as strong as that of water. The other thing we need to consider is the shape versus the size when we're looking at melting point and boiling point. If we have a molecule that looks like this, and here generally we're looking at organic molecules. Organic molecules can get really big, and their shape is actually more important because they're all mostly nonpolar or very low polarity. So the two basic shapes we're going to look at are long, skinny molecules or spherical molecules, relatively speaking, blobs. So if you look at those two, which one do you think would have a higher melting point, higher boiling point? Something that's fairly round or kind of clumpy in shape, or something that's long and skinny in shape? Think about it a minute. It turns out that these particles, when they combine to form solids, so we're looking at melting points here, we're going to get a structure, solid structure, where we've got a bunch of spheres in contact with each other, like so. These structures are going to look like a stack of pancakes. Now, what keeps these things as solids is the intermolecular forces that hold them side by side. If we look at the pancake stack, we've got all this surface where there are intermolecular forces holding the two molecules together. It's a lot of holding power, even if the London forces are pretty weak, because that tends to be what is holding those molecules together. If we look here, if I'm dealing with spheres, I really only have one place where the spheres are in contact and therefore can make attractive forces hold the other one nearby. So I got a lot of attractive forces on the pancake stack, and I have roughly one attractive force holding the spheres where they make contact. So it turns out because of that, my pancake structure is going to have higher melting points and boiling points. The reason for that is there's a lot of contact. There's a lot of opportunity for intermolecular forces to hold the molecules together. If I look at the spheres, I have lower melting points and boiling points.